All right, so now we're going to get into the real physics of the course, okay? So finally, we're starting the physics. And to do that, we need to talk about, first we talk about vectors and scalars. And if you had grade 10 science, if you were actually one of those lucky ones that had it first semester last year, and if you were in French science, you would have heard these two terms. If you were in English science, maybe not. And I don't know why it's in the French curriculum and not the English one, but that's the case. Okay? And really, vectors and scalars are two categories that everything we talk about in physics would be put into one or the other. Kind of like we could look at everything in the world and we could say it was animal, vegetable, or mineral, right? When we could categorize like living, but by like living like a dog, a cat, a person, or growing like a plant, or rocks, desks, chairs. So every quantity that we use in physics, like displacement, velocity, acceleration, force, time, temperature, all energy, all those things, all of them are either a vector or a scalar. Okay? So first let's start off with the scalar. And I do have a sheet of notes that I will post in the handouts. But most people learn better if they write notes down themselves. You probably know enough about how you learn, or I hope you do, to know how to take notes, but I would recommend that you might want to take your own notes just because we tend to learn better when we write it. Goes through or stays in our brain longer, maybe, I'm not sure. So a scalar quantity is a quantity that simply is a number, simply a number with a unit. In other words, the number means it has a size, or we often use the word magnitude, and a unit. Like how much mass does that apple have? It's a half a kilogram. It has a size. It's 5 degrees outside this morning. It has a size with a unit. It took me 10 minutes to come to school. Okay? All of those things are perfectly described when we give the number and the unit. So some examples are time, temperature, mass. Okay? How far do you live away from the school? 6 kilometers. Distance is a scalar. Okay? The other one, vectors, vector quantities. A vector quantity then is something that not only has a number with a unit, but it also needs a direction. So it has magnitude, right up there we said magnitude with size, magnitude with unit, and a direction. Now I could have asked you before we started if we were in person, how many of you heard the word vector before? And a number of you would have said yes because of grade 10 science, but some of you would have said yes, and when I asked where, you would say, well, it's a brand of hockey stick, or it's a cereal, or it's one of those energy granola bars. But from now on, when you think of a vector, I want you to think of an arrow, because that's what a vector is. It's an arrow. And this long part is called the shaft, and the length of the shaft gives us a sense of the size of the vector. And then the direction that the arrow is pointing tells us the direction. So this might be something like 2 meters per second east. Whereas this vector, which is longer and going, and it might be 3 meters per second north, right? So the longer the vector, the longer we'll make the shaft, and then we'll try to point the arrowhead in the direction of the vector. Okay? So when it's a vector quantity, it's not completely described unless we put the direction in. So for example, force is a vector. And maybe I have a box sitting in the hallway, and I say to two of you, you know, if you each push on that box with 100 newtons force is measured in newtons in physics, in metric, if you each push on the box with 100 Newton force, you'll be able to move it down the hall. And I walk away, and so two of you decide to test this out. So one of you pushes with a force of 100 newtons this way, and the other one of you pushes with a force of 100 newtons this way. Obviously, this box is not going anywhere because force is a vector. I needed to say, okay, you both need to push with 100 newtons force in the same direction. Okay, like both to the right or to the east. Right now, you're not going anywhere because those are going to cancel each other out. What are some other examples of vectors? So examples are acceleration. Which way is gravity going to cause you to accelerate? It's 9.81 meters per second squared down. You never have to worry about which way is gravity going, the vector gravity going to act. It's always going to be downward. Other examples would be velocity, and we just said a minute ago there force. Okay, and there's more that we'll get to. Now, if you think, if someone could say to me, can you tell me how to get to Woodstock from here? And I might say, well, if you go to the Princess Margaret Bridge and get on the old highway, then from there, if you travel about 110 kilometers per hour for an hour, you'll be in Woodstock. Well, maybe, or you might be in Sussex, right? I didn't say go west on the highway. If you don't go west, you're not going to get to Woodstock. So vector quantities need a direction. Okay? Now there's some really important rules then that go with vectors. Because the direction matters, when we're adding and subtracting vectors, we need special rules. So adding vectors. Now these special rules for the first couple of cases will be like borderline common sense. Case 1 is when the vectors are acting in the same direction. And if vectors are acting in the same direction, and maybe I'll use force here just because it'll be easier to see. So we take my box and we had 100 newtons going this way east, and I'm just going to change the other one to maybe 3, oops, that looks more like 200 newtons east. Okay? Borderline common sense, because you should be able to look at this and tell me what are you going to get if one person's pushing with 100 newtons east and the other's pushing with 200 newtons east. Hopefully you're saying 300 newtons east, and that's correct. The rule is add and keep the direction. Add and keep the direction. But whenever you're adding vectors, they need to be put in what is known as head to tail. Sorry, the box I'm resting on, this iPad on, isn't very sturdy. So you need to put them head to tail. So here's my 100 newtons, and then I need to slide my 200 one, so the tail of the 200 is lying on the head of the 100. So I'll put it in here. And then the resultant starts where the first one started and ends where the last one ended. And so if I was adding 20 vectors together, I would still do exactly that. I would just line them up, all up head to tail, and then start where the first one started and ends where the last one ends. This vector is called the resultant because it's the resulting vector from adding them together. And so the rule is add and keep the direction. So this would be 300 newtons east. That's case 1. When they're going in the same direction, we say there's 0 degree angle between them, right? If you had a protractor and you lied it along there, it would be at 0. That's case 1. Case 2 is also borderline common sense. Case 2 is when they're going in opposite directions. I'm going to run out of time here. Okay, so we have our box. We have our 100 newtons going east on this side. And on this side this time, whoops, imagine that straight, would you? We have two